等多2分鐘啊！等多少少同學入嚟，我哋開始啦。有啲同學好似話嗰個功課嗰度，好似佢想多少少時間嘅，咁我 extend 到下個禮拜一，份功課 extend 到下個禮拜一，咁你哋可以下個禮拜一先交啦嚇。唔使多謝，咁啊仲唔使俾多啲時間啦。嗱，但係咧考試下一堂咧，我今堂會講晒㗎啦，嗰啲要講嘅 chapter。咁咧下個禮拜咧就會同大家溫一溫啲重點啦，同埋提一提醒大家要溫嘅地方。咁所以下個禮拜大家都要上喎。咁即係可以重點溫翻一啲比較重要嘅地方啦嚇。咁考試咧要做得快㗎，因為咧都有8條大家要做㗎嚇，即係有 Part A 同 Part B 咁都多嘅。咁所以大家除咗要識做之外，都要訓練翻個速度，唔好太慢啊。同埋咧，我想問咧，你哋係應該係分咗組噶嘛？係咪啊？你哋做個 lab report，咁你將嗰啲 lab 嗰啲組咧，你 send 翻個組名俾我。如果唔係，我唔知你個邊個打邊個一組啊。你 send 翻個組名俾我，你用 email send 俾我啊。邊個係邊組？咁你有個 student 嘅名同埋個 ID，咁你自己分咗組，你 send 翻俾我啦。即係上次嗰張嘢好似唔係好齊啊，最後都唔係個個同學個名分咗組。收到啊，Sir。好啦，咁我哋都開始住先啦嚇。上次咧，我哋就講過一個方法咧，都係講過叫做一個俾 indeterminate 嘅 structure 做嘅 moment 嘅方法啦。咁咧個方法咧，我哋叫做 moment distribution 嘅方法。咁咧呢個方法咧就係最主要咧，我哋會 assume 嗰啲 moment 咧會喺個 join 之間咧係會傳嚟傳去啦。咁depend on 佢有幾硬淨啦。通常越硬淨嘅 member 咧就會越攞得多 moment 嘅，越腍嘅 member 咧就會越攞得少 moment 啦。咁所以咧其實 moment distribution method 咧都係一個方法啦，去分析咧statically indeterminate structure 嘅。咁咧佢就會用到一個叫做distribution factor 嘅概念啦，即係咧啲 moment 咧會喺個 join 之間咧互相傳遞啊，即係話咧如果加咗喺一個 join 嗰度嘅時候咧，會根據佢 stiffness 咧去傳個 moment，去睇下點樣傳去俾兩個 member 嘅。咁個 distribution factor 咧基本上咧會根據嗰個我哋叫stiffness factor 啦嚇。去分配個 moment 嘅，咁我 stiffness 我個 member 咧就係4個 EI 除 L。一般嚟講咧，我哋用呢個方法咧去評估嗰條 member 咧有幾硬淨嘅。OK，E 就係個材料啦 ，Young's modulus 啦 ，I 就係佢個 cross section 啦 ，L 咧就係佢長度啦。咁當然啦，如果你個物料越硬嘅，咁你個 stiffness 就越硬啦，係咪？ I 係講個形狀 ，OK？ 咁某啲形狀咧係會硬淨啲嘅，個 I 大啲嘅形狀就硬淨啲啦。而 L 嘅話咧，越短嘅 member 咧，佢亦都越硬淨嘅 ，OK？ 咁個 distribution factor 咧，基本上咧係你考慮嗰個 member 嘅 EI over L 啦，除翻 total 嘅4個 EI over L， 即係咧我哋用個比例嚟分啦，即係黐埋喺同一個 join 嘅，譬如我假設呢度3條 member， 1號仔、2號仔、3號仔，譬如我有個 moment 加喺個 join 度嘅時候，有幾多去咗個 member 1，幾多去咗個 member 2，同幾多去咗 member 3咧，我就用個 EI over L 嚟分啦 ，OK？ 好，咁樣咧，我哋上次咧都試過做過一條 member 俾大家睇，點樣去分力啦。咁我呢度咧都做多一條 example 啦，大家可以參考下啦。譬如我呢度有條陣啦，咁我呢度咧有個 support 啦，我呢度咧有個 support 啦。咁假設呢度我有個 point load 篤落嚟啦，咁我假設呢個係10個 kN， 然後假設呢度有個 distributor load 啦，呢度咧係5個 kN per meter。咁最後嗰度係冇 loading 嘅。咁方便起見啦，我全部都用10米啦。咁一個 EI 咧都係一個 constant 嚟嘅，即係佢中間個 EI 都冇變啊。咁個 member 咧我叫 A、B、C、D 咁先算啦。嗱，如果做呢個咧，我哋首先第一步咧，我哋要揾佢嘅 fixed end moment。咁我哋會簡稱做 FEM。咁咧，我哋要揾喺左邊同右邊嘅 fixed end moment 啦。嗱，我哋而家呢度咧有兩種 type 嘅 loading 嘅狀況，一個咧就係一個 point load 嚟嘅。如果中間有個力加落嚟，呢個係 P 啦，而呢度有個長度我叫 L 啦。咁呢度咧會有個 fixed end moment 喺左邊，呢個叫 A，呢個叫 B 啦。我都有個 fixed end moment 喺右邊叫 BA 啦。嗰個 fixed end moment AB 嘅話咧就叫做 PL 除8。咁咧我哋要當 clockwise 係正嘅，咁所以你睇下呢個 moment 咧，左手邊呢個 moment 咧，由於佢係 counter clockwise，所以我哋會寫佢係負嘅嚇。咁 fixed end moment 咧喺右手邊咧，我哋為之正啦。嗱，記住呢個正負咧，同你個 bending moment 本身正負咧係兩件事嚟㗎嚇。因為咧你用呢個方法嘅時候咧，我哋會當個 moment 係正嘅話係 clockwise。咁一陣間我會試俾大家睇係咩意思㗎啦。轉言之，你睇到而家呢個 moment 咧係 counterclockwise 嘅話咧，咁我哋當係負數啦。好，另外咧，如果我有個 fixed end， 另外咧我有個 distributor load 加喺上邊嘅話咧，假設個 distributor load 我叫 W， 有個長度叫 L 嘅話咧，咁喺兩邊嘅 moment 咧，假設呢個又係 A， 呢個又係 B 啦。個 fixed end moment 喺左手邊咧，就叫做負 WL square 除12。咁喺右邊咧，就叫做負 WL square。sorry， 應該係正 W square 除12咁樣嘅意思。好啦，咁我哋要做呢條陣嘅時候咧，我哋就想揾喺個 member 嘅尾個部分呢個 moment 係幾多？咁如果係咁樣咧，我哋首先咧都要畫個表嘅。咁我做呢條嘅時候咧，我哋首先因為你睇到有4個 join 啦，所以我哋首先寫嘅時候咧會寫 join A、B、C、D， 即係我有4個 join 位喺呢度。而咧我跟住咧有 member， 我咪有 member 嘅 A、B 啦，因為咧你睇下4個 join 嘅時候咧，呢4個位置係 join 啦。 咁而 join 咧呢個位置咧有 member AB，呢個 member BA，呢個 BC，呢個 CB，呢個 CD 同埋呢個 DC，呢4個位置sorry，呢6個位置我要寫翻出嚟㗎嚇。所以我寫 AB 先啦，然後寫 BA 啦，然後寫 BC 啦，然後寫 CB 啦、CD 啦同埋 DC 嘅。咁我有呢6個位啊。其實我 moment 咧有呢6個位置嘅 moment。咁我就會間開啲線咧俾佢嘅。好啦，好似上次咁講啦，我一開始會當所有嘅 join 係 fix 先，咁我就會 develop 咗個 fixed moment 喺嗰度，然後我要加翻個 balance moment 喺嗰個位置嘅。所以咧呢度咧我會考慮個 distribution factor 啦。頭先都講啦，如果喺個 join 度我有個 moment 加咗落去嘅話咧，就呢個位置係個 join 啦。呢個位置我個 moment 加咗落去嘅話咧，佢其實會 distribute 去前邊同後面嘅，咁就睇下支 man 擺有幾硬啦。佢用4個 EI over L 嚟分嘅。咁而家我哋嗰個 EI 又係一樣，個長度又係一樣。咁所以如果我有個 moment 加喺呢個 join 度嘅話咧，一半就會分喺前邊，另一半咧就會分喺後面啦。咁所以咧，我 distribution factor 嚟講咧，呢度都係0.5，呢度都係0.5嚟嘅。咁喺 C 嘅位置亦都係啦，兩個位置都係0.5啦。而如果兩邊係長嘅話咧，呢度係埲牆啦，呢埲係埲牆啦。咁佢個 moment 咧就會俾埲牆食咗㗎啦。咁所以咧，我哋呢度 put 係0就可以啦。咁我哋咁樣寫啦，呢個 distribution factor。好啦，然後咧，我哋當我哋鎖死晒所有個 join 先，咁我哋就會 develop 咗一個叫 fixed moment。咁如果照做嘅話咧，我哋呢個 P 今次咧就係10個 kN，呢個 L 咧就係10米。OK。咁所以如果呢個我照做嘅話，就係都係-100除翻8，呢個就係-100除翻8，咁就等於12.5嚟嘅。呢個就係-12.5。所以咧呢個位置咧就係-12.5啦，同埋咧12.5嘅。而 WL square 咧呢個位置咧，我哋今次個 W 係5啦，然後個長度係10啦，除翻12。咁呢個亦都係5乘10嘅 square 除翻12。如果你照計嘅話咧，呢個係等於41.6。咁所以咧，我哋會喺度照寫-41.6啦，41.6嘅。咁而最後呢個 span 咧，我哋係冇 loading 加上去嘅。咁所以咧，我哋個 fixed moment 咧，就算我 fix 咗兩邊都好，佢個 moment 係0嚟嘅。所以咧，我就會寫咗個咁樣嘅關係出嚟，有冇問題？好啦，一陣間做嘅嘢咧，好機械化嘅啫。你寫到呢幾行出嚟之後咧，就其實係一啲機械性嘅計數嚟嘅啫。嗱，幾個步驟嘅啫。嗱，而家有個 moment 喺左手邊12.5喺個 join B 嗰度啊，右手邊有個-41.6嘅 moment。好啦，如果我要將呢個位置加晒佢嘅話咧，12.5減41.6，你用我計數機撳一撳，咁你就會撳到咧。我撳一撳啊。咁你就會撳到係-29.1㗎啦，即係將12.5減41.6。咁咧，即係話你要而家有個-29.1嘅 moment 咧，係加咗個 join B 嗰度。嗱，無端端嗰個位置咧有個 moment 咁係唔啱㗎，所以咧我哋要加翻個正嘅29.1喺嗰度，咁先至可以 balance 翻個 moment 嘅。因為我上次都講過個 join 其實唔係 fix 㗎嘛，我哋人為咧將佢 fix 咗。咁而家咧要將佢 balance 翻，咁所以咧 而家有個負29.1喺度啦，咁所以咧我哋就要人為加翻個29.1喺度啦。咁但係一加落去個 join 度嘅時候咧，一半會去左手邊，一半會去右手邊，因為我 distribution factor 係0.5啊嘛，係咪？所以咧我就會有一半走去左手邊14.55，另外一半咧就走去右手邊。你可以睇翻咧，其實咧呢個位置咧係個 hinge 佢哋自己 balance 咗嘅，所以咧呢個叫做 distribution，即係咧個 moment 咧會喺即係29.1咧會喺兩個 member 之間 distribute 咗，加埋之後咧你將呢4個 number 加埋係0嚟㗎嚇。好啦，咁啊做多個啦，睇 John C 啦，佢有41.6喺度啦，咁個 moment 無端端有個41.6喺度喎，咁唔得㗎嘛，你原本係冇 moment 㗎嘛。咁咧，我哋就要加翻一個相反嘅 moment 落去啦。咁如果啱啱要抵消嘅咧，就加翻個負20.3喺度。因為咧，我哋個 distribution factor 每邊係0.5，所以咧每邊係減20.3。如果你睇翻呢個咧，呢個 join 自己本身咧，全部加埋咧，呢四個數字加埋係0嚟嘅。咁呢個都係0啦。咁我哋就做完啦。好啦，上次我哋都話啦，如果我有個 moment 加喺一邊咧，另外一邊咧，我會 create 到一個同樣方向，但係個力度係細一半嘅 moment，我哋嗰個叫做 carry over moment。咁所以咧，我就會 carry 一半過去對面嘅。咁 carry 咗一半過去對面咧，將14.5除2咧就係7.28。咁啊，呢個就7.28啦。20.3嘅話咧，你 carry 過一半就所以20.8啊，應該-10.4除翻一半，係嘛？咁樣咧，你個 join 咧重新咧有個新嘅 moment 啦，喺 join B 嗰度咧就有個負10.4喺度啦。咁無端端有個10.4喺度，應該話負10.4喺度，咁唔得噶嘛。咁你就要加翻10.4喺嗰度。但係一加10.4咧，一半會去左手邊，一半會去右手邊。一樣啦，7.28，咁你要減翻一個 moment， 7減7.28加7.28先等於0。咁一半去左手邊，一半去右手邊，咁就負3.64。咁樣呢個又係 distribute 啦。好啦，distribute 完咧又 carry over 咯喎，因為有個 moment 咧，佢就會揈過隔離啦。係咪啊？好啦，又係咯喎，咁你而家 carry over 咗之後咧，你又要 distribute 啦。負1.82，咁你就要加翻個1.82啦。左手邊一個，右手邊一個。咁2.6咧就負1.3啦，所以每邊咧都有個負1.3喺度嘅。distribute 之後咧又 carry over 啦。咁啊呢度變0.46啦。咁咧呢度咧就變負0.65啦。0.46啦。咁啊負0.65啦。好啦，整完呢個之後咧，你又 distribute 啦。咁啊0.65嘅話咧就0.33啦，每邊。咁啊呢個負0.23啦，每邊係咪？咁你話喂，咁一路做落去唔係辦法喎，嗱，做多2個算啦。咁啊負0.12啊，呢度就係0.17啦，即係 carry over 啊嘛。carry over 咗之後咧，又 distribute 啦。 嗱，我哋咧做到呢度算啦。咁呢度係負0.09。嗱，最後咧個 join 咧都係 equilibrium 嘅，因為呢度啱啱都係零嚟噶嘛，係咪？呢度啱啱都係零，所以咧我哋一定咧係停喺 distribute 呢個位㗎嚇，就唔好停喺 CO 嗰個位啊。carry over 咗之後個 moment 咧都係 unbalance 嘅。好啦，如果你做到呢步咧，咁就差唔多完啦，即係話分個 moment，你又將由頂節體由個 fixed moment 呢一行開始。一路加晒咁多個 call 咁多行嘅 moment。咁如果你由頂至底加落去咧，第一個佢就會負1.91啦。咁第二個咧，你如果就由12.5加14.5加5.2加0.91加1.33sorry 加0.33再加0.06，你一路加晒落嚟嘅話咧，佢應該就係33.55嚟。另外一邊都係啦，你將負41.6加14.55減10.4加5.2減1.82加0.91減0.65加0.33減0.12再加0.06，你就會得到呢一個同呢個基本上一樣咁大嘅答案。嗱，有時候可能爭少少嘅，譬如呢度33.55。一邊係負33.54，嗱爭少少咧，我哋算㗎啦，因為有時係嗰啲數字嘅進位嘅問題，咁所以呢啲大家唔需要擔心啊。哎呀，唔係 exactly 一樣，咁唔需要擔心，因為係小數後兩個位嘅基本上，嗰啲我唔會去即係去挑剔㗎啦。咁另外咧，另外一個由41.6開始減20.8加7.28減3.64一路做到下面咧。你就會加到出嚟咧係26.05，而另外一邊咧，如果你做到個數字基本上係差唔多，基本上都係26.0幾㗎啦，咁就係負數嘅話咧，咁即係話咧係啱嘅，因為咧你兩邊應該係一樣係 balance 㗎嘛，係咪？咁另外咧，你再加嘅話呢度咧就將負10.4減1.82減0.65減0.12全部加埋晒一齊，咁就係負12.99啦。咁你所有嘅 member 嘅尾嘅 moment 咧，基本上咧你已經揾咗出嚟㗎啦。咁你話喂，咁我咁樣做完，咁跟住點啊？其實做完呢個嘅話咧，你就已經成功在望啦。咁咩意思咧？頭先即係話咧，正負嚟講咧 ，clockwise 嚟講咧，佢為之正嘅。咁即係話咧，如果畫翻條陣啦嚇，一開始佢負，即係話個 moment 係咁啦，1.91個 kNm，咁咪呢度篤落嚟啦，有個10嘅 kN 啦。另外嗰邊咧係正嘅，即係正嘅 moment 咁啦，33.5個 kNm。咁呢個係第一個 member 嘅 moment。第二個 member 咧，負數先，負33.5。你呢個負唔可以唔寫喺度都得，因為咧你個方向咧已經係證明咗佢係負㗎啦。咁你上面有 distributed load 啦，頭先我哋係5個 kN 啦 ，meter 啦。咁另外呢邊咧又係正26.05，正即係 clockwise，所以就正26.05啦。而你再嗰邊嘅話咧，就冇 loading，咁佢兩個都係負數嚟嘅，即係兩個咧都係 counter clockwise。咁就26.06 kN 同埋12.99 kN。有冇問題？即係你照住個 member 個尾嘅 moment 咧，你就可以畫翻晒呢啲出嚟。OK？ 咁嘅話咧，其實你個 member 個尾仲有啲 shear 嘅，我哋譬如叫 VA 啦，呢個位置我哋叫 VB 啦，呢個我哋位置都叫 VB 啦，呢啲我叫 VC 啦，呢個我哋又叫 VC 啦，呢個我叫 VD 啦。嗱，費事將兩個 VB 溝亂咧，我喺度加翻個 dash 俾佢啦。好啦，咁我哋咧用 equilibrium 咧就可以揾晒啲 VA 啊、VB 啊、VB dash 啊、VC 啊、VC dash 啊、VD 出嚟嘅。咁點樣揾咧？我諗大家都識㗎啦。不如由 section AB 開始啊。咁我哋咧呢個位置叫 A 啊，呢個位置叫 B 啦嚇。呢個位置叫 B 嘅 C， 由 C 去 D。好啦，咁你都知道 summation of moment 咧 ，A 一定等於0嚟㗎啦。咁我就將1.91啦，減33.55啦，減10乘5啦，因為呢個位置咧係5個 meter。咁你就計到咧，sorry， 仲漏咗個 VB 啊。咁你就會計到個 VB 咧係8.16個 kN， 而 VA 咧就係等於1.84個 kN。OK， 咁你從個 free body diagram 咧，你可以揾埋兩邊嘅 shear 係幾多。咁section BC 都係啦。咁咪一樣啦 ，take moment 喺 B 啦。咁33.5係正數啦，減26.05係負數啦，就再減5乘10，再乘5，又係負數啦，再加 VC 乘10，就等於0。咁如果你將啲數調嚟調去咧，你就會揾到個 VC 咧係等於24.26，而 VB 咧就等於25.74。有冇問題？我哋呢個叫 VB dash， 因為佢係咁樣。咁我哋最後嗰個 section CD 亦都係咁樣做啦。咁睇到我兩個 moment 咧，其實佢轉嘅方向係一樣，都係正嚟㗎嚇。好，咁樣咧，我哋條式寫咗啦，我哋可以揾到個 VD 咧係10。呢個 VD 應該係向下㗎，因為咧 VD 向下，我先可以 create 同 VC dash 一齊 create 個相反嘅 moment 咧，去對抗嗰個 member ends moment 啊。個 VD 揾咗出嚟咧，就係3.9個 kN， 而 VC dash 都係 3.9個 kN， 有冇問題？咁我哋就揾晒啲 shear force 同埋 bending moment 出嚟㗎咯喎。咁咧，如果你想揾翻個 support reaction 都得嘅，譬如話你有個 support 喺 B 啦，咁如果你睇翻呢個 support 喺呢度啦，呢個 support 喺呢度啦，其實咧佢就有個 moment 向兩邊咬啦，都係33.5啦。咁你兩邊咧都有個 shear 篤落去啦，都係 action and reaction pairs 啦。所以咧個 support reaction 咧就會係 VB 再加 VB dash 嘅，所以就係8.16再加25.74啦。我哋將佢加埋咧，就係33.9啦。咁另外嗰邊嘅 support 亦都一樣啊 ，C 個位置，兩邊都係26.06。個 support reaction 咧都係 VC 加 VC dash 啊。咁你睇到咧 VC 係24.26啦 ，VC dash 係3.9，即係24.26。再加3.9，咁就28.16。咁我哋根據呢啲咧，我哋就可以畫個 shear force 同個 bending moment diagram 嘅。咁或者畫個 shear force diagram 先啦。呢度5米啊，呢度10米。20啦。OK，咁個 shear 咧一開始咧，如果我哋睇到呢度一開始咧上嚟個 VA 咧就係1.84嚟嘅，咁所以咧我哋一開始有個1.84嘅 shear。到中間嘅位置咧，我篤落去向下篤10嘅，因為咧我有個向下嘅 loading，篤落去10個 kN 啊嘛，係咪？所以咧佢就會變咗8.16。喺下面啦。到呢度咧，去到 support 度咧，我突然間有個33.9，因為我頭先計出嚟啦，呢個 support reaction 33.9向上啦。咁所以咧有個向上嘅 loading 啦，基本上喺10米嗰度就變咗25.74。好啦，跟住咧中間咧我個 distributed load 向下，然後咧你睇到個 distributed load 咧係5個 kN per meter，total 個長度係10米，所以咧佢就會跌咗50個 kN 嘅 total。咁所以咧就會變咗24.26啦，負24.26。 咁呢個位置咧，即係15.15嚟嘅。上到嚟呢度之後咧，我哋又有個 support reaction 28.16，咁上翻嚟呢度啦。一個24.26，再減翻28.16。咁即係去翻咧3.9。個 shear force diagram 咧就畫佢出嚟啦。識唔識畫？嗱，呢啲咁樣咧係 typical 㗎嚇，你要識得畫嘅。咁根據個 shear force diagram 咧，我哋就會畫個 bending moment diagram 出嚟。一開始你睇到佢有個向下嘅 moment 嘅係咪？咁呢個 moment 咧就係一個負嘅 moment 嚟嘅，負1.91，即係個向下咬係咪？咁所以咧就有個負1.91個 moment。嚟到呢度咧，佢係一個正嘅 moment 嚟嘅。咁咧佢就會係上升幾多咧？就會係呢個 area， 就會係佢個 moment increment。所以將1.84乘翻5，再加負1.91，咁你就會計到係7.29嚟。下一個咧就要減翻上面個長方形嘅 area 啦。咁你可以計下一個，譬如話計呢個長方形嘅 area 啦。由於佢喺下面咧，所以5乘1.86咧，就係佢呢個長方形嘅 area。咁啊減去7.29上面嗰個。如果你減咗之後咧，睇到個 slope 咧係一個負 slope 嚟嘅，所以咧佢就會向下跌。咁如果你減咗個 area 咧，就會發覺咧，佢挫到落負33.51。咁跟住咧，你計下一個三角形嘅 area 啦。你睇到呢個三角形嘅 area 咧，佢由正一路跌翻去0嘅，即係個數字。咁即係話咧，其實佢會正縮啦，然後佢會跌翻去0嘅。咁個 moment 具體加幾多咧？就係個 area 嚟。咁你將25.74乘翻呢個距離啦，呢個距離咧其實係5.15嚟嘅，即係將25.74乘5.15再除2咧，就會係呢個三角形嘅 area。咁就再加翻上負33.51，你就會計到上邊嗰個哚哚係幾多噶啦。如果你計完之後咧，應該咧你就會得到個結果係32.77。你下一步咧就要減翻隔離嗰個三角形嘅 area 啦。咁你就將5.15啦，即係10減5.15，即係4.85。你將4.85乘翻24.26，再除2咧，就係呢個三角形嘅 area。咁如果你咁樣揈完之後咧，你就會發現咧，佢咁樣揈落嚟啦。佢揈到嘅回收咧係負26.06。而你最後咧呢個 area 咧就會係佢個 moment 上升嗰個 area。咁最後咧，因為呢個 slope 係正啦，所以你會正向上啦。然後咧，你最後嗰個 moment 咧，你睇到呢個 moment 咧就會係12.99，所以咧最後會喺12.99嗰度停。 咁就完整咁畫咗個 shear force 同埋個 bending moment diagram 啦。有冇問題？呢個就用個 moment distribution 咧去做出嚟嘅，得唔得？嗱，呢個咧係用個你可以睇到啦，呢個係一頭一尾咧都係 fix end 嘅時候咧個做法。咁有時候咧，我哋就有一條陣咧，我哋就會去到一個情況咧，就係個尾咧，有時候咧唔係 fix end 嚟，有時都係個偏 support 嚟。咁咧就我哋咧就會用一個簡化啲嘅方法去做。譬如話，假設呢度有個 loading 啦，咁譬如會咁樣，咁我哋點樣做咧？咁我諗大家可能啱啱做完嗰個都有啲攰啦，我哋休息幾分鐘，跟住翻嚟咧，我哋試下做呢個。呢個咧就係當嗰個 member end support 咧係 roller 或者係偏 support 嘅時候一個做法。OK，一陣間轉頭介紹一下俾各位。 嗱，到時候咧一個類似咁樣嘅 fixed moment 嘅表咧，就會 provide 俾各位嘅。咁所以咧，你可以喺入邊查翻啲 fixed moment 點樣揾啦嚇。咁嗱，我哋就頭先都用咗左邊第二個啦 ，WL square 除12啦，呢個係咪？咁如果係 distributed load 嘅，咁我哋可以加翻個loading 落去啦，即係兩邊係 WL square 除12啦。咁如果係 point load 嘅，我哋頭先就用咗呢個啦 ，PL 除8啦。咁就係我哋頭先做嗰個嚟嘅。嗱，記住喺任何情況底下咧，我哋其實都用兩邊 fix 嘅嚟揾個 fixed moment 㗎嚇。只有一個特別嘅 case 就係你最尾嗰個 support，如果係偏或者係 roller 嘅時候咧，你就會用呢個 case。嗱，最尾係偏或者 roller，你睇到呢度。咁嘅話咧，個 moment 咧就會係3PL 除16，或者係我哋個 case 啦。個 moment 咧就會係 WL square 除8嚟嘅，所以一陣間就會用呢個 WL square 除8嚟做個 moment 嘅。咁所以你睇到呢度啦，我哋 A、B 嗰個 span 咧就係冇 loading，所以個 fixed moment 咧就係冇嘅。咁頭先咧我哋睇到有個 case，如果我 fixed 一邊，然後咧呢個係個位置，然後咧呢個係個 roller，咁我加個 distributed load 嘅話咧，我 fixed moment 喺度咧就係 WL square 除8。咁由於佢係 counterclockwise 啦，所以係負數嚟嘅，得唔得？咁我哋就用呢個咧去計。嗱，右手邊咧，由於佢係一個 roller support 咧，就唔會有 moment 噶啦。咁所以咧，我哋可以慳翻右手邊嗰個 support。但係最後個位置如果係偏嘅話咧，咁佢個 member 個 stiffness 咧，頭先我哋話用4個 EI 除 L 去做嗰個強度啊，用嗰個硬度。咁嘅話咧，我哋而家咧就唔會用4個 EI 除 L 噶啦，我哋咧最尾嗰個如果係即係最尾個 span 啊，如果係roller support 嘅話咧，我哋就唔用4個 EI over L，我哋咧就用3個 EI 除 L 就得啦。嗱，具體點樣實現咧？我做一次俾大家睇呢度。嗱，假設有個 moment 咧，一陣間要加下 B，咁佢會 distribute 去 BA 同 distribute 去 BC 係咪？咁所以咧，我哋會有個 distribution factor。我哋會有個 distribution factor 咧，係 distribute 去 BA， 亦都有個 distribution factor 咧，係 distribute 去 BC 嘅。咁點樣做咧？頭先我就話一般嚟講咧，我哋計其他 member，我哋一定用4個 EI over L 嘅。假設呢個 EI 都係 constant 啦，即係左邊同右邊個 member 嗰個E 係一樣嘅，個 I 都係一樣嘅，唔同即係個長度嘅啫。嗱，左手邊個 member 咧都係普通嘅 member，所以咧我一樣用4個 EI 除 L 去做，咁咧就 AB 個 size，咁咧就 total 個 EI over L 咧就寫喺下面。右手邊嗰個咧，由於佢個尾咧係roller support 啦，所以我哋用3個 EI 除 L。咁嘅話咧 ，EI 就互相取消啦。咁我用4除翻 LAB 就係5啦。咁呢個4除5啦，再加3除5啦，咁樣計嘅。咁大家都係5底啦，所以就係4除7。OK。咁剩低咧 BC 咧就一定係1減4除7。 咁咧我哋就用3除7就搞掂啦。咁我哋好少用份數嘅，我哋就寫翻做小數位啦。咁4除7同3除7，我大家撳一撳啦。咁就0.57。咁呢度底係0.43。好啦，咁我哋點樣做咧？一樣好似頭先咁，用個 join A、B、C 寫一次。咁我 member 喺呢邊啦。咁A、B 喺呢度啦 ，B、A 喺度啦 ，B、C 喺度啦 ，C、B 喺度。同頭先一模一樣嘅啫，都係要寫晒呢啲先。嗱，不過咧，由於佢係個 roller 喺另外嗰邊咧，我哋就唔會 distribute 啲 moment 過去噶啦。咁我會畫一畫。咁呢度咧係4，呢度係0啦，因為呢度貼牆啦。咁呢個係0.57，呢個0.43。即係如果有 moment 分落嚟嘅話咧，57% 會喺左邊，43% 會喺右邊。OK。至於 fixed moment 咧，我係第一個 span AB 咧就冇 moment，因為我冇 loading 擺落去啊嘛。而另外嗰邊咧，我就有一個 moment 係 WL square 除8。咁我哋呢個 case 個 W 係5啦，個長度係5嘅 square 啦，除8。即係話咧，我將5乘3次除翻8，咁就係15.625。咁我寫15.63。好啦，咁同頭先一樣啦。做完之後咧，我哋 distribute 佢。咁有個負15.63喺度啦，咁我要加翻個正15.63啦。咁先 balance 啦。咁但係咧5乘7咧會去左手邊，咁所以咧就8.91。15.63減翻8.91，咁就6.72。你可以睇翻呢個 join 自己本身咧已經 balance 咗㗎啦。咁我哋下一步咧就 carry over 過對面。右手邊呢個唔使 carry over 啦，因為咧佢嗰邊唔係 fix 嚟嘅，佢嗰邊個 member n 咧係個 roller，所以我哋唔使射過去。咁所以4.45，咁就做完啦。因為咧我哋冇新嘅 moment 咧去落去我哋嘅 join B 嗰度，而 C 亦都唔會有 moment，所以咧做一步咧就已經做完啦。所以個 moment 咧就係4.45。咁呢度係8.91，呢個係負15.63，再加6.72，負8.91。咁呢個冇嘢啦。咁所以咧呢個就會有個正嘅 clockwise 嘅 moment， 4.45。呢個都係 clockwise 8.91 kNm。再過嚟咧就有個 moment 喺呢度啦，8.91，再加個 distributed load 就5個 kNm。咁當然啦，我哋要揾翻啲 support reaction 啦，好似頭先我哋咁樣。 有冇問題？咁揾翻啲 support reaction 或者 shear 咧，呢啲我就交翻俾你哋做啦，都係 equilibrium 啫，係咪？咁嗰啲就唔困難嘅。咁嗰個咧我就唔喺度繼續介紹啦。OK， 有冇問題？OK， 咁如果冇問題咧，我哋可以繼續講埋我哋剩低嘅部分。咁我哋一個部分咧就係 moment distribution 嗰度仲有啲未講完啦，就係喺frame 嘅應用。咁另外咧有一課咧我哋叫 approximate analysis， 咁咧就會講埋。咁基本上咧我哋呢個成要包嘅課程咧就差唔多係完結啦。Last one we have mentioned about the moment distribution, and then I have just illustrated the way how to perform the moment distribution method, and then to analyze for the continuous beam. And the last one we have mentioned about an example here, and then to show you how to deal with an example if we have a so-called the cantilever or the hanger beam. And then using the same way, actually you can see here we can solve for the answer for a hanger beam. And then for this one, actually it is quite straightforward. And then afterward, you find the member ends moment. Then using the equilibrium, you can find for the shear force. And then you can draw the shear force and then the bending moment diagram accordingly. And then as we mentioned just in the tutorial, if you have the end support as a roller support or as the pin support, instead of using 4 E alpha L, you will use 3 E alpha L to simplify your calculation. Then you can find the bending moment using another type that not both sides are the fixed, while one is fixed and then the other one is actually the roller support or the pin support. Then use that one to simplify your calculations. For other cases, actually you can ignore them because actually it is just for your reference. Say for example, if you have a beam like this, actually we have illustrated a similar one in our tutorial. Then actually you remember that you will choose the bending moment using this type because it is WL squared over 8. And then don't use this one because this is both sides are the fixed end, okay? You should use this one because the end support is the roller support. Then by using this one, actually you can simplify your calculations and then you can determine your member ends moment immediately. And then you can use the so-called the equilibrium equations to find the shear force at the member ends, and then also find the support reactions. And then finally, you can plot your shear force and then your bending moment diagram. So this one actually we have already illustrated in the tutorial. And actually the moment distribution method can also be applied to frames. And then this is actually one with the no sideway for the frame. Well, actually we just use the same procedure, and then they can also be applied to the frame. So for example, you can see that we have a frame here, which is actually have no sideway reactions. That means when you apply the load, as actually there's a constraint at the location E, so your frame will not deform literally. So it is actually a frame with no sideway. So for this example, we want to determine the internal moments at the joints of the frame as shown. There's a pin at the E and the D, and then it's a fixed support at the A. So right here, we will use similar way to find for the moment. So for here, actually, you have a fixed end moment at the location B, and then you have fixed end moment at the location C. You will check the fixed end moment accordingly, and then find it by WL square over 12. And then you can see that you will distribute the moment among the member AB, BC, CD, and then the CE. Then you will use the stiffness factor KAB, KBC, KCD, and KCE as shown. Now, because A is a fixed support, so you will use 4EI over 5. And then for BC, you can see that actually this is just similar to what we have done before for internal members. We also will use both sides of fixed ends. So it is 4EI over L. And both the support D and the support E are actually the pin support. So we will use 3EI over L. So you can see that we use 3EI over L here, and then we use 3EI over L right here. Because these are pin support, and then these are also pin support. Then for the DFAB, actually it is equal to 0 because it is the fixed support here. So all the moment will be absorbed by the fixed support. While for the BA, then you can use the so-called stiffness factor of BA here, and then over the sum of the stiffness. So you use 4EI over 5 divided by 4EI over 5 plus 4EI over 6. So these two is the sum. And then you will put this one as the denominator. I mean numerator. Then after finding DFBA, then you can find for the values of BC, you just have 1 minus this value because this value belongs to this member. And then for the other members, actually you just use 1 and then minus the the distribution factor. Then you can find the value 0.455. Similarly, you can find DFCB and then you can find DFCD. Then you can see that because this join, there are 3 members joining. So actually you will have, when there's a moment applied at the joint C, then you will have a portion distribute to the CB, distribute to the CD, and then distribute to CE. So you have the distribution factor to CB, CD, and the CE, okay? So you can see that 33% will be distributed to CB, 29.8% will be distributed to the CD, and then 37.2% will be distributed to CE. And then you can see that basically just the span BC will be fixed end moment. So don't worry about that. This question mark is actually just means kilonewton meter. Okay. So you have WL square over 12 on the left hand side for the BC, and then for CB again it is WL square over 12. So similarly, we will write down a table like this. So first of all, you would write down join A, B, C, D, and E. And then of course you will have the member AB, and then you have BA, and then the BC, and then the C, you will have CB, CD, and CE. For the distribution factor, well, actually, as I mentioned, at the location A, actually it's the fixed end. So actually, all the moment will be absorbed by the fixed end. At the location B, then the moment will be distributed to the side BA and then the BC. And then at the joint C, it will be distributed to three members. We will distribute to CB, CD, and then the CE. So for this one, you have three distribution factor here. While D and E is actually a pin support, so basically no moment will be distributed or carry over to the pin support. So first of all, you can see that at the BC, you will have two fixed end moment. And then within this joint, actually, they will be in equilibrium. For the joint B, actually 135 negative is the moment. And then you need to apply 135 to the joint B in order to balance this negative 135. And then 54.5 will be goes to the left-hand side, while 45.5% will go to the right-hand side. So you use 135 times 0.545, then it is equal to 73.6. And then the remaining is 61.4. And then for the joint C as well, you have 135 here, and then it will be distributed to the three members. So in order to balance the moment, then you have to apply negative 135 to the joint C. And then you can see that 33% will go to the first member. And then 0.298 will go to the second member, and then the last one will be 50.2. After the distribution, you need to carry over to the other side. No need to carry over to D and the E, because actually they are the pin support, so you don't need to carry over to the other side. So you can see that there's nothing here because actually they are pin support. Then you will repeat the process until the values are very small. Then you will add all of them together, and then you can find that the moment is equal to 44.5 at the AB, and then BA is equal to 89.1, and so on. So accordingly, you can draw the bending moment diagram for the frame structures. So basically, this is for the frame. And actually, the method can also be applied to a frame structure with sideway. Now, first of all, I would like to mention that for the frame with sideway, it is not in our scope of study, basically, because it is a bit tedious for you to find the answer. So here I will just demonstrate to you how to find the solution, but I won't put it in the examination because it is too tedious for you. So, but at least you need to know the way how to solve for the answer, okay? Now you can see that for the frame with sideway, that means when you apply the load to the frame, then it will deform literally, that means horizontally in this case. So you can see that because you apply the load in unsymmetric condition, so the frame will actually deform in the horizontal direction. And then that means it will have the sideway. That means it will deform literally of the frame. And then for this one, actually, how we can analyze our structures? Well, actually, we can use a method of superposition. And you can see that for the first frame, in order to restrain the movement of the frame, we will apply a support right there and make the frame to be no sideway, and then we apply the load. But you can see that the frame actually is not restrained laterally. Okay, so well, actually, in order to show the original case, we need to apply R to the right-hand side in order to eliminate the effect. So to find all the member ends moment, we need to add case 1 and case 2 together. Okay, then I can find the the moment in our frame. Okay. So for here, I have an example, and then to illustrate the idea to you. So we want to determine the moments at each joint of the frame shown here, and then for here, EI is a constant. And then for here, we assume that there is a support at the location C, which restrain the movement of the frame. So for this one, again, we will find the fixed end moment at the section BC right here. We can check it from the table as shown before. And then we will carry the carry out the so-called the moment distribution as before. So you can see that we have our fixed end moment, and then we will distribute our moment among the joint, and then carry over to the other side. And then we will distribute our moment among the members and carry over just like what we have done before. So this one is actually the very similar to our previous process. And then afterward, you can see that you have the member ends moment here. And then you can determine the shear force according to the equilibrium equations. And then you can see that there's a 1.73 kN pointing to the right-hand side, while there's a 0.81 pointing to the left. So if you are taking a look to the summation of Fx is equal to 0, then you have 1.73 pointing to the right, and then you have 0.81 pointing to the left. That means actually there's a force, the force difference of 1.73 minus 0.81. So the force is actually equal to 0.92. That means actually there will be a reaction force which is equal to 0.92 acting as a support in order to balance the horizontal force at the member ends. Otherwise, the summation Fx will not be equal to 0. Okay. So from here, we can find that actually the resisting force at the joint C is equal to 0.92. Okay. Then afterward, we should apply the force at the corner C, of course, in the reverse direction, and then find the member ends moment. And then afterward, we will add the two moments together to find for the answer. Now to do that, actually, first of all, we assume that there will be a fixed, we assume that there will be a horizontal deflections at the joint B and the C. And then we assume that it will cause a fixed end moment at the members A, B, and then the CD. So you can see that we assume that there's a delta dash implied at the joint B and the C, which will create a moment, negative 100 kNm at the member ends of AB and CD. And then by assuming that, actually, you can see that we have the fixed end moment at A, B, C, and D. Then again, we will carry out the so-called moment distribution method. And then you can see that we find all the member ends moment. And then from the member ends moment, actually, we can derive what is the horizontal force on the structures. And then if we apply the deflection, and then assume that there will be 100 kNm of the moment developed in the members, actually, when you add AX and the DX together, the force is equal to 56 kN. That means if it will create a so-called 100 kNm of the fixed end moment at the ends of the members, then actually the horizontal force will be equal to 56 kN. But instead, actually, we just need 0.92. So as you can see here, we do not need to use the whole member ends moment, but we will use a fraction of 0.92 divided by 56. And then 80 is the member ends moment when the force is equal to 56. So we just do it by proportion. We just have 56 as the denominator and then 0.92 as the numerator. and then times 80, while 80 is the member ends moment. And then this is actually from the case 2. And then this is actually the moment from the case 1. So we just have the case 1 and then plus case 2, and then that's how we can get the member ends moment afterward. And then for each of the member ends, actually we do the same, and then we can find for the answer. But you just need to know about the way how to find for the moment for frame with sideway, okay? But don't worry about that because we won't put it in the examination. This one is too tedious to be an exam type questions, okay? But of course, you still need to know the way how to solve it, okay? Okay, so this is actually the end of the moment distribution. And then finally, I will go to the final chapter, which is actually, we call that is the approximate method for analysis. So this is the last chapter. We call that as the approximate analysis of statically indeterminate structures. So we will talk about the use of approximate methods for truss, and then for vertical loads on building frames, and then for portal frames and truss. And then finally, we will introduce 2 commonly used methods. One is portal method and the other one is cantilever method. And then we can use them to estimate the loads in our frame structures, okay? So here, why we need to use the so-called approximate method. Like you learned from the previous topics, basically we can solve for all the answer of within the structures by using equilibrium equations, or if we have more unknowns than the number of equilibrium equations, actually we need additional compatibility equations from the structures. Then, well, it can be a very tedious analysis and then time-consuming analysis, actually. But actually, in many cases, for engineers, we will have the so-called the initial design. The initial design basically are still in the preliminary stage. And then when we have the shape of the structures or the rough idea of the structures, actually we do not know what is the member size to be used. So at this stage, actually it is not necessary to have a full analysis of our structures. Instead, actually we can build a simpler model, and then the result is actually approximate, say for example, 80 to 70% of the accuracy, so that the engineer can guess or can estimate the size of the member based on the approximate analysis. So actually this is always for the engineers for determination of the size at the initial stage. So for this one, actually it is also important because this actually gives the engineers an alternative way to solve for the answer without going into too detailed analysis. Otherwise, actually we put too much time for preliminary design, which is actually not necessary. So actually, we will have some assumption to simplify our structures from our indeterminate structures to our determinate structures, so that we can find all the results by just equilibrium equations. Then we can estimate our size accordingly. This is actually the objective of using approximate analysis. But for here, for the truss, as you can see here, this is actually a truss with indeterminacy, because you can see that this is not a simple truss. You have quite many diagonals, okay? So if you count the number of unknowns and then count the number of equilibrium equations, you will find that actually it is an indeterminate truss with the degree of indeterminacy equal to 3. So we cannot just solve for all the answer by using the equilibrium equations. then you can see that if we cut a free body at the location AB, actually you can see that there will be several member forces. You have F1, F2, and then you have FA, and then have FB. But if you treat the truss as a beam, then actually you will have a vertical shear at the truss panel. Then when your support reaction is equal to R1, then actually there should be a panel shear which is equal to R1 again, which is acting downward. So for here, actually we have three indeterminacy. I mean the degree of indeterminacy is equal to 3. So basically we need 3 assumptions in order to make the determinacy equal to 0. So for here, actually we can have 2 methods to adopt and then to reduce our degree of indeterminacy. The method 1 is that, if you still remember, we have 2 bracing, or we can call it as a diagonal. Now this diagonal basically is longer than our horizontal or vertical member because they are in the diagonal. And when structures actually it is long and slender, basically it is reasonable to assume that they cannot support the compression force, because you can think that it is long, and when it's subject to compression force, it is slender, and then it's easy to buckle. So the first method is that the compressive diagonal is assumed to be a zero force member. We can assume that the diagonal or the bracing member, which is having the compression force, it may actually carry zero force right there, because we assume that compression is to buckle and then it carries no force. For the method 2, actually we can assume that, well, because actually one of the bracing actually is taking tension, while the other bracing actually is taking compression. You can go back and then take a look. When you have the force here, as I mentioned, when the force pointing away from the member, it is a tension. When the force pointing towards the member, it is compression. So for here, one of the diagonal will be in tension, and then the other one will be in compression. And then, well, for the method 2 is that we can assume that actually they equally capable of supporting a tensile and compressive force. That means we assume that the force in the diagonal are the same. Both of them are equal to F. And then actually they are responsible to carry the panel shear together. So half of the shear is taken by the tension diagonal, and then half of the shear is taken by the compression diagonal. So this is the way how we can simplify our truss member. So for here, we will demonstrate to you how to simplify our indeterminate truss so that we can find the solution quickly. Right here, determine the forces in the member of the truss. The diagonal are to be designed to support both tensile and compressive forces. That means right here, diagonal like FB and then the AE, EC and then the BD, we assume that both of them carry the same load, and then actually they carry half of the shear. Okay, that means the force in AE and FB are the same, and then each of them actually responsible for carry half of the panel shear. So for here, you can see that we have the load 10 kN here, 20 kN here, and then for the support, we have 20 kN here and then 10 kN here. Okay. So for here, we will cut again the free body and then take a look. Well, you can see that this is actually statically indeterminate structures with the second degree. And then we can assume that when we cut the free body diagram, we assume that both of the force within the diagonal is equal to F. And then actually, both of them are responsible for resisting the shear, 10 kN here. So we are considering the summation of Fy going up is equal to 0. And then vertically, we have 20 kN, and then we have 10 kN going downward. And then right here, actually, we have F here. You can see that the slope is 3, 4, and 5. If we consider the vertical component, then it is actually 3 divided by 5 and then times F. So you can see that 3 divided by 5 and then times F is a vertical component. Of the panel of the diagonal force. So we assume that both the diagonal actually taking the shear. So we will times 2 here. So 2 times the vertical component of the diagonal force will be equal to the V. So we have 20 minus 10, and then minus this one is actually the V. And then which implies that the force within the diagonal is equal to 8.33 kN. Then the FFB is actually pointing away from the member, from the joint. So actually it is a tension force. So here, this one is a tension. Well, the one pointing towards the joint, actually this one is in compression. So you can see that in a very quick way, we have already found the values of forces in the diagonal. And after that, we will consider the equilibrium at different locations. Don't worry about that here. Again, we will use summation. And then this is the bracket. This is the bracket. Now, this is summation. This is implied. Now, don't worry about that because in your notes there will be no problem. Just in the PowerPoint, it shows some error here. Then, well, you just take the moment at the A. So you take moment here, and then you can find the values of FFE. Right here is simple. You have the values of 8.33. Actually, it is in the diagonal here. This is 8.33, and then you consider the horizontal component. So you divide it by 5 and then times 4. So here is the horizontal component. Horizontal component. Of the diagonal force. Okay, and then you have FFE times 3. So